set this up here. All right, so we got to the point where we said that the rate of a reaction is equal to the rate constant K times the concentration of the reactants raised to some power M or N or whatever you want to call them. Those are referred to as the order of the reaction. Okay? And they're usually whole numbers, but they don't have to be. Sometimes you can have an order of 1/2, for instance. Where this is. Sorry. They clearly made these for men's shirts. Okay. So we were using the method of initial rates to actually determine the rate law expression for a reaction. The method of initial rates, we basically use a number of different experiments where we're changing the concentration of the reactants and then determining the initial rate. And we said that if we hold the concentration of one of the reactants constant and we vary the other, we can see how the rate changes, and that'll help us to figure out the order for the reaction. So for determining M, which is the order with respect to ClO2, we can change the ClO2 concentration, like in experiments 1 and 2, and hold the hydroxide concentration constant and observe the initial rates. Okay. And then to determine the order with respect to the hydroxide ion, we can use experiments 2 and 3. Sorry. Okay. So there is a way where you can figure out the order simply by looking at how the initial rate changes when you change the concentration of the reactant. I don't necessarily recommend that you do this when you're starting out with these problems. I recommend what I'll show you next. But I do want you to know that this is a possibility. So for instance, where we double the concentration of the reactant, we can see how the rate changes. If the rate is doubled, when we double the reactant concentration, the order will be 1. Okay? If we double the reactant concentration and the rate is quadrupled, the order is 2. Okay? It's a factor thing. So if you double 2 and then you see that it's quadrupled, in order to get quadrupled you have to square it, so that's where this 2 is coming in. But like I said, it's sort of something that you practice. It's hard for me to teach how to do it. It's something I've been doing for a long time, and so I can just sort of see this happening, and I think you will get there with some of the easier things. But you don't have to do that. Okay? You can use the equation that's shown in the box, where we find the order. In this case, I left it as M. You take the log of rate 1 over rate 2, divide by the log of the concentration of 1 over the concentration of 2, where 1 and 2 are experiment numbers, or it could be 2 or 3, or 1 and 3, however it is. And so when we tripled the concentration of ClO2, erase. ClO2, we've tripled the concentration. We go from 0.02 to 0.06 moles per liter, holding OH minus constant. We actually see that the rate goes up 9-fold. Okay? You can plug these in. So rate 1 would be 0.0248, rate 2, 0.00276, concentration 1 would be 0.06, concentration 2 would be 0.02. Do all your logs, divide this out, and you should end up with 2. Do the same thing holding the ClO2 concentration constant, and you'll find that the order with respect to OH minus is 1. And so we triple the concentration of OH minus, and the rate triples. Okay. I will say, I do recommend practicing using this equation. It won't be given to you on the exam, all right? But I think this is one that's relatively easy to remember. It's rate over rate, concentration over concentration, take logs. You can tell me I'm crazy. But practice with this, I think it'll start to come naturally too. Okay. So this is just the table from the previous slide using the same reaction, and we experimentally determined the order for each reactant. And now what we can do is solve for the rate constant K. All right, and the way we do that is we plug in data from any of the experiments. Okay, and I'm going to set my equation equal to the rate constant K. So we'll divide both sides by the concentrations of reactants. And we'll have rate, and that's the initial rate, is equal to the concentration of ClO2 squared times the concentration of OH minus raised to the first power. And I'm just going to take the data from the first experiment. I guess I should make sure I'm doing it correctly, math-wise. Okay, so we'll take 0.0248 moles per liter per second and divide by 0.06 squared times 0.03. Okay, and I end up with a rate constant of 230 moles per liter to the -2 times seconds to the -1. So the units on your rate constant can be a little funky, and it's all dependent on the exponents that are showing up in the rate law. Okay? Make sure you can follow through on the units. I guess I got a little messy here. This is moles per liter on the bottom. So we have moles per liter per second in the numerator, divided by moles per liter squared in the denominator. No, cubed. So that's moles per liter times seconds to the -1 times moles per liter to the -3. You guys remember all this rules for exponents? This cancels. Okay, some unit analysis for you. Okay, questions on this? All right. So kind of summarize here. If we're looking at how the magnitude of our rate constant affects the rate, actual rate of the reaction, a large value for the rate constant K will mean that the reaction is occurring fast. And a small value of K, it's a slow reaction. And once you know that rate law expression, you can solve for K, you can determine its units. And again, just to summarize, the reaction order, those are the exponents, the M or the N, what have you. And there's another term here that we use, it's called the overall reaction order. And that's simply the sum of the exponents. So M plus N plus whatever. Okay? So for the previous reaction, we had an exponent of 2 and an exponent of 1. The overall reaction order would be 3. Okay. Yes?
So what's the importance of the
What's the importance of the overall reaction order? That's a great question. This is one of those things that if you're working on homework problems, they may give you the overall order, give you one other thing, and you have to figure out the rate law expression. In terms of real life chemistry, I don't have a great answer for you because this isn't really my specialty. I'm not coming up with rate laws while I'm doing my research, so I apologize for that. I can actually take a look and see how that's being used in the real world. Okay. Any other questions? Okay. Oh, yes.
A large scale, how do you know,
What's large and what's small for K? Just comparatively. So you might see a problem where you're given two different rate constants and it wants to know which reaction is occurring more quickly. Yeah. There's no cutoffs or anything. Cool. Anything else? Okay, so I'm going to have you guys work on this problem. I'll come around, see how you're doing, making sure you can get started, things like that. So we've got a reaction with nitrogen monoxide and hydrogen gas. Assuming it's gases, let's assume gases. And you need to know the rate law, so you're going to have to determine the exponents, and then go ahead and work on determining the rate constant K. All right. Getting started. Any questions? You guys okay getting started over here? You guys all right up here? Okay over here. Yes, any questions? Everyone all right back here? How did I do that? Undo. Feel free to work with your neighbors. some ahas.
Maybe. I think I messed. They're not both 2. This one is quadruple. Or, yeah, so this one should be 4, not.
Yep.
Yeah. So that kind of screws it up a little bit. So this might be 4? I don't know. With the math. Maybe not.
You're doubling the concentration. Right?
Wait, no, dang it. That was one line. So this one's 4, this one's 4, this one's 2, this one's 2. Correct.
What you doing? This is the thing from the book. You do it differently than I do.
I'll see if I can do the same thing.
Yeah.
Squared divided by.
All right. Questions?
So when it comes to the balanced chemical equation,
Yeah.
does that have anything to do with putting in the rate? Do we have to calculate the relative within the bracket?
No. So always make sure there is a balanced chemical equation.
Yeah.
Let's assume that that's the case. But it doesn't really affect the exponents necessarily. So even though there's a 2NO and 2H2, those don't really have any bearing. Right.
Thank you.
Yep. You guys doing all right? You getting it? Doing good? Yes.
I think we should have the last example that you went over.
Mhm.
It said that, like, for the answer, it was
Yeah.
like n to the negative 1 and like s.
Yeah.
Can you explain like why it was so negative? Because it's only the numerator. And it was
So I think we had moles per liter per second in the numerator, and then moles squared in the denominator, moles cubed in the denominator. When you pop that up, it becomes a negative exponent, and then that canceled with the positive 1. So it's,
What about the n? Yeah.
oh, it should still be there, s minus 1. It doesn't change.
Oh, so it's always like s minus 1, like two problem.
Yeah, because, let me switch back real quick. Whoops. Whew. All right, so what did we get for the order for with respect to NO? 2? Does everyone agree? So we used experiments 1 and 3, okay? And when we double the concentration, it looks like the rate is quadrupled. And so that is an order of 2. Feel free to use the math, the equations, like I said. Again, this is practice. Yeah?
So when I put in the equation in, I'm not sure if I was getting it right, but can you put the concentration of the experiment 1 over the concentration of experiment 2?
So it can be,
So would it be log of 0.1 over 0.1? Or
so it's, if for the concentration, it's the one that's changing. So 0.1 over 0.2.
so it's always the one that's changing?
Always the one that's changing, yeah. So if you end up with log of 1, you've done something wrong for the concentration part. Yep. And what about for the order with respect to hydrogen? 1. That's what I got as well. I can't erase. It's just some things I just don't quite get. Okay. Okay. So now you take the data from one experiment, and to find the overall rate, and so you just take data from one of the experiments. K equals rate, initial rate over concentration of NO squared times the concentration of H2. Plug in concentrations from one of the data, one of the experiments, rate from one of the experiments, same experiment, solve for K. And you should get the same rate constant no matter what experiment you put in there. And so I ended up with 1.23 moles per liter molar to the -2 and seconds to the -1. Anyone else get that?
Yep.
Okay. Cool. Have this on the other slide. Yep. I didn't actually work it out. So we are finding K. So then we can use our rate law with our rate constant to describe the rate of change for any reactant or product in our reaction. And so if we say that the concentration of NO is 0.25 molar and the concentration of H2 is 0.2 molar, we can determine the rate, overall rate, just by plugging in these concentrations and our rate constant. And our units should cancel, so we should end up with moles per liter seconds. Make sure you square the NO concentration. And I end up with a rate of 0.0154 moles per liter per second. So now we can use our comparative rates to determine how the production of one of the products or the disappearance of one of the reactants is affected. So for instance, I think I have, yes. So our overall rate is 0.0154 moles per liter per second. Using, if you remember from last time, we said that we take 1 over the stoichiometric coefficient times the change in the concentration over time, change in time. And we can relate all of our reactants and products. So now we can do that and determine the rate of N2 production, H2O production, the rate that NO is consumed, and the rate that H2 is consumed. So the only really interesting one, so if we look at our stoichiometric coefficients, they're all the same except for N2. Okay, so let's look at the rate, what the rate that N2 is produced at. So I'm just going to use our stoichiometric coefficients to relate. So we have 1/2 times the change in concentration of NO over the change in time equals the change in concentration of N2 divided by the change in time. And so we know our overall rate, 0.0154. And so we can plug that in. Sorry, I had a moment. Let's say that our rate is equal to the change in N2 over the change in time, because that's the one with the stoichiometric coefficient of 1. Hang on. I'm confusing myself here for a sec. Just give me 1 second. Yeah. Okay. I'm actually going to look at the rate that NO is being consumed. So we want to find change in NO over the change in time. And that's equal to 2 times the change in N2 divided by the change in time. And we know this value is the 0.0154. And that's simply because of the stoichiometric coefficient up here. Okay. So we should find that NO is being consumed at 2 times 0.0154, which is 0.0308 moles per liter per second.